Hello everyone, I am glad to share with you our work, Masked Image Training for Generalizable Deep Image Denoising. When capturing and storing images, devices inevitably introduce noise. Reducing this noise is a critical task called image denoising. Deep learning has become the de facto method for image denoising, especially with the emergence of transformer-based models that have achieved notable state-of-the-art results on various image tasks. However, deep learning-based methods often suffer from a lack of generalization ability. For example, deep models trained on Gaussian noise may perform poorly when tested on other noise distributions. To address this issue, we present a novel approach to enhance the generalization performance of denoising networks, known as masked training. Our method involves masking random pixels of the input image and reconstructing the missing information during training. We also mask out the features in the self-attention layers to avoid the impact of training testing inconsistency. Our approach exhibits better generalization ability than other deep learning models and is directly applicable to real-world scenarios. Additionally, our interpretability analysis demonstrates the superiority of our method. Next, I will elaborate on our work in detail. Image denoising is a crucial research area that aims to recover clean images from noisy observations. Deep learning networks are trained using images synthesized from a predefined noise distribution and can achieve remarkable performance in removing the corresponding noise. However, a significant challenge in applying these deep models to real-world scenarios is their generalization ability. The noise distribution in the real world can differ from that observed during training. More specifically, most existing denoising method trains and evaluates models on images with Gaussian noise, limiting their performance to a single noise distribution. When these models are applied to remove noise drawn from other distributions, their performance drastically drops. We illustrate the generalization problem of denoising networks here. We train a SwinIR model on Gaussian noise with sigma equals 15. When tested on the same noise, SwinIR demonstrates outstanding performance. However, when it comes to out-of-distribution noise, example, the mixture of various noise, SwinIR suffers from a huge performance drop. The model trained by the proposed masked training method maintains a reasonable denoising effect, although it is also trained on Gaussian noise. We argue that the reason for the poor generalization ability of the denoising models is that our training method makes the model focus on overfitting the training noise instead of learning the image reconstruction. We conduct a simple experiment for verification. We trained a SwinIR denoising network using images that greatly differ from natural images, immunohistochemistry images. We synthesize training data pairs using Gaussian noise, and then assess the model's performance on natural images with Gaussian noise. The results are presented in figure. As observed, the SwinIR trained on immunohistochemistry images can still denoise and reproduce the natural image. This supports our conjecture regarding generalization ability, indicating that most existing methods perform denoising by overfitting the training noise. Consequently, when the noise deviates from the training conditions, the denoising performance of these models declines significantly. This observation also inspires our approach to developing deep denoising models with improved generalization ability. We aim for the model to learn the reconstruction of image textures and structures, rather than focusing only on noise. In this paper, we propose a new masked training strategy for denoising networks. During training, we mask out a portion of the input pixels and then train the deep network to complete them, as shown in figure. Our approach emphasizes reconstructing natural image textures and edges observed in the image, rather than overfitting noise. The input mask randomly masks out the feature tokens embedded by the first convolution layer, and makes the network complete the masked information during training. The input mask explicitly constructs a very challenging in-painting problem. The attention mask. There is inconsistency between training and testing. We can narrow the gap between training and testing by performing the same mask operation during the self-attention process. Here are the performance comparisons on 4 different out-of-distribution noise types with different levels. All models are trained only on Gaussian noise. Our masked training approach demonstrates good generalization performance across different noise types. We involve multiple types and levels of noise in testing. The results cannot be shown here. More results are shown in the supplementary material. This is the visual comparison on out-of-distribution noise. When all other methods fail completely, our method is still able to denoise effectively. Please refer to the supplementary material to see more visual results. Next, we will present additional results to substantiate our generalization performance. This figure shows the training curves of the model with and without the proposed masked training. The models are all trained using only Gaussian noise. The baseline method has a significant overfitting problem. The performance of our method gradually improves with training without overfitting. We also visualize the distributions of deep features on different noise types. We can see that for the baseline model, the feature distributions under different noise types vary from each other significantly. For the model with masked training, the deep feature distributions of different noise types are close to each other. This confirms the effectiveness of our method. Thank you for watching.